Welcome everybody to this webinar on medical physics. We want to show you how medical physics can be used to improve lives through science and innovation, both in medical imaging, diagnosis and treatment. My name is Pilar Garcia Soto. I am a professor for teaching in the UCL Medical Physics and Biomedical Engineering Department at UCL. And I'm joined here by a range of excellent researchers that work here in the department, and all together we hope we are going to tell you a little bit about medical physics so you understand this field a little bit more. Also some of the work that we do in the department specifically, and how you can start your journey in the field if by the end of the seminar today we manage to um, inspire you. Next. So the question is, what is medical physics? The field and the work of medical physics is actually very present in our lives. Medical physics refers to the scientific field that applies principles of physics and science to medicine, especially for the diagnosis, treatment, and even prevention of diseases. It is responsible for many advances in medicine, from a simple finger pulse oximeter to intricate magnetic resonance imaging scanners or complex linear accelerators for radiotherapy, or even proton therapy for difficult cases of cancer treatment like in the brain or in children. But its use and advances also expand beyond the field of healthcare, as we will see today with some examples. Um, with research focusing on developing new or improved medical imaging techniques, diagnosis, physiological monitoring, and the development of implanted devices and treatments, the field of medical physics offers the excitement of discovery and the reward of contributing to human well-being. And that's why it is, is one of my favorite fields to work in, because it actually taps into two of my favorite things. Next. So the UCL Department of Medical Physics and Biomedical Engineering, is a reference, is a referent in the field of medical physics. There are various reasons why this is happening. For a start, we are very strong in research, and we are at the forefront of the state of art in many areas of medical physics. Some examples like the ones that you will see later. We are also one of the longest established and largest departments that teach medical physics in the UK, and we are very good at it, if I have to say so. We also have extensive connections with a range of stakeholders and networks. So connections with engineering, connections with the physics department, and also plenty of connections and ties with hospitals, since we work with them very often, and we actually feed from each other. We also consider our students an integral part of our department, and we engage them into, well, with them benefiting and contributing to our research during the entire of their studies. And they actually get integrated into the research teams that we have at our department. Next. So just as an example or a teaser, some of the areas of research that we work on are medical imaging, with ongoing research in all the major modalities of imaging that you can find at a hospital, either for diagnosis, but also for interventions like when doing image-guided surgery. We do research in physiological monitoring and all the varieties of it. And we have strong research in development of medical treatments like photon therapy, but also medical devices like implanted devices for neuromodulation. And of course, being at the front of development in these areas, we also use AI and machine learning when needed and when suitable. Therefore, our field really offers the excitement of discovery and the reward of contributing to the human well-being. So it's quite, I find it quite motivating, really. Next. So it is a big field. It will be impossible to show you everything that we can do within medical physics or all the contributions that medical physics have done to human well-being, throughout the decades. But today, at least we want to show you some examples directly from our researchers in things that are happening at the moment. And I hope that you find them inspired. So we are gonna start with Professor Sandro, if we go to next slide, who's gonna talk us a little bit more about his research. Sandro.
Thank you, Pilar, and good evening, everyone. I'm Sandro Olivo. I am an applied physicist, and I work in X-rays, which are sort of old stuff because they've been around for now 130 years. So some people wonder, can you still do more stuff with X-rays, new stuff with X-rays? Does it make sense to do research in that area? And the answer is a resounding yes, as far as I'm concerned, especially because of machines like these that you can see in the background. They're called synchrotrons. They're quite big. They're roughly as big as a football stadium, but they generate X-rays of a new type that enable you to do things that up to a few years ago were considered to be impossible. Next slide, please, Camilla. And this is one example. It's a very simple example and a very early image, but here you can see on the left-hand side conventional images of objects that are basically X-ray transparent, very, very hard to see, like a small flower or an insect. But by using these new machines, we can transform the image quality from what you see on the left to what you see on the right-hand side. So the amount of detail that you can now visualize from things that were considered to be invisible is sort of impressive. Next slide, please. So we started to try to use these sort of new capabilities of X-rays on humans, and we've done clinical trials inside the synchrotrons, for example, on mammography, by scanning patients using these sophisticated X-rays inside these machines. This worked very, very well, and we got some amazing results. But the issue was that so long as you need to use a synchrotron, then you're very much restricted in what you can and cannot do. There's only about 50 synchrotrons in the world. Next slide, please. So what my group did is to develop systems. You can see an example here on the top of the slide, whereby using conventional equipment, and with that I mean X-ray sources like those that you would find in a hospital, that would enable you to do the same thing, to create images of the same quality. And there's an example here, which is like a small image of a beetle. But if you press the next slide, Camilla, please, it will zoom in. And then you can hopefully see that there's a lot of very fine detail visible, like the hairs on one of the hind legs. So this really shows you that you can now, with some sort of engineering development, create the same type of images, high quality images. We call these phase-based images that were only possible in specialized facilities using conventional equipment. Next slide, please. So what do we use it for? Well, there are several examples. At the synchrotrons, where the technology is more advanced, we have been able to image entire humans. With these machines, can we go back one? I don't know why it's proceeding. Apologies about that. We've been looking into examples where we image smaller things, but still with an impact on patients and society. One typical example is what we call intraoperative imaging. So here, the issue is to try to image specimens that are resected from a patient during a surgical operation. And very often, you need to see inside these specimens to make sure that you've removed the entire tumor, for example, if this is an oncological operation. At the moment, this is done with conventional X-rays, and it gives you images like the one that you see on the left-hand side, very blurry, very unclear. And then the specimens are sent to a pathology lab. that basically stains and sections these tissues, looks at it under a microscope, and then you get the image on the far right, the pinkish violet image. In that image, you can see pretty much everything, but this only becomes available after a week or two. So if you see something there, then you'll have to call the patient back for another operation, which, as you can imagine, is very, very bad. So we can now create images like the one in the middle, which is much, much better than the one on the left, which is what was available before, and starts to become really similar to the one that you see on the right-hand side. The idea being we can now provide this information in real time during the operation, so that if more tissue needs to be resected, it can be done there and then without the need to call the patient back. Next slide, please. Another practical application is, you may have heard of biopsies, which is when the doctor removes a very small bit of tissue with a needle to check it under a microscope and see whether there is some sort of disease involved, typically cancer, but not only. And the image on the left-hand side, the small one in pink, is what typically a pathologist would look at under a microscope. If you take that image and you convert it to grayscale and you compare it to one of our images, you'll see that our image on the far right, and I call that phase CT, on a microscopic resolution, here we see every single cell and every nucleus, is pretty much the same as the histology image, almost enhanced. But then you can transform it. If you press one more, Camilla, a volume should appear. There you go. And if you press again, maybe it shows different orientations. You press one more time. Oh, it skipped. It doesn't, okay, the video doesn't work, but it doesn't matter. So the message is that this is now 3D. So effectively, the doctors can now see all the information that they need in all directions, in all dimensions from a single scan, instead of having to suction tissue. And I think I'm running out of time, but very quickly, I have two more slides. One more, Camilla, please, is to show that there's many other, or maybe this is the last one, so it's very quick. There are many other applications of the same technology that they're not medical. So on the left-hand side, bottom left, you see two images of what you call a composite material, which is very important in aerospace and transport industry. 50% of a modern airplane is made of these materials. They're very difficult to test. And what we demonstrate with the greenish image at the bottom is that with our method, we can see defects and blemishes to an extent that is invisible to conventional techniques. And on the right, you have an example in security scans, like baggage screening at airports, where we show that we can detect very faint traces of explosives hidden inside complicated items like electrical items in very small quantities, better than current systems can do. So there's sort of innovation across the board, mostly medical, but not only. And I think that is me done. Thank you, Pilar, and everyone, and Camilla. Oh, yeah, of course, this is the group, recent photos, some of our funders, and a couple of links if you want to contact us in the future in case you want to know more. Thank you.
Okay, thanks so much. So I'm going to talk a little bit about using some new MRI methods to map tissue electromagnetic properties for clinical applications, and I'll explain a little bit more what I mean by all of those things. Next, please. Oh, thank you. Okay, so this is just a little overview of my career, taking me from playing with magnets and iron filings at school. Perhaps some of you have done these kinds of experiments. I did an undergrad degree in focusing on physics, then trained in the NHS as a clinical scientist, and did a PhD at UCL. Went to the USA to do some postdoctoral research, came back to UCL, and have stayed at UCL since 2012. Next. So what is MRI? Well, MRI stands for magnetic resonance imaging. And the magnetic part refers to the fact that we're using a very, very strong magnetic field. That's tens of thousands of times the field that we're all sitting in, the Earth's magnetic field that turns a compass needle. And this creates a tiny, tiny signal, a tiny, tiny net magnetization when you're in this MRI scanner from from the nuclei of the hydrogen atoms in your water molecules in your body. We excite a signal using radio waves, and we use the phenomenon of resonance, which is a physical phenomenon. So we can detect this tiny signal by exploiting this resonance at radio frequencies. And then we turn these tiny, tiny signals into very detailed images, as you can see here on the left. So that's a very, very brief overview of what MRI is. Next, please. When we are what we're researching is electromagnetic tissue properties. And the interesting thing about what we do is that 99% of the time, the images that you will see from MRI are from what's called the magnitude of the signal. So just the size of the signal. And this signal is actually a complex signal, which means it's a bit like a complex number. It has a magnitude, excuse me, and a phase. But most of the time in conventional clinical imaging, the phase images are just thrown away. We don't even bother saving them. But all the work that we do is actually rescuing this phase, taking it out the bin, and getting some really useful information out of it. So what do we do with these phase images that look a bit messy here in the middle? Well, we can calculate two different properties of tissue from these phase images. The first property is this one on the left, called magnetic susceptibility. And the method that we use to calculate this has a complicated name called quantitative susceptibility mapping. So I'm going to call it QSM for short, just because it's quite a mouthful to say that every time. And the reason we're interested in this susceptibility is because it's related to the actual ingredients in the tissue. And these are the kinds of things that change when there's disease processes happening. So for example, there are changes in iron content in different diseases, or in myelin content, or in calcifications. And so getting a map of the magnetic susceptibility of the tissue might give us insight into those disease processes. Click, please. The other property, the other electromagnetic tissue property that we can calculate from these messy looking phase images is the electrical conductivity. So this is something that you're probably more familiar with just from, thinking about wires and conductivity and resistance. But actually this is interesting because it's not the conductivity when you put a direct current through the tissue. It's the conductivity that is there at very, very high frequencies. So at these radio frequencies that we're using in MRI. And this is interesting because it tells us about the ion content in the tissue. So does the tissue have a lot of sodium ions or potassium ions? Because these things also change in disease. So looking at these electromagnetic tissue properties should help give us insight into different disease processes in the body, not just in the brain. Next, please. So why, I've said a little bit about why we're interested in these properties, but just to give you a bit more of an example of this. So susceptibility depends, as I've told you, on the ingredients or the chemical composition inside the tissue. And what we've found, particularly in the brain, is that we've got different major contributors to the magnetic susceptibility of the tissue, and those things change in different diseases, so that gives us different clinical applications. So for example, we have changes in the stored tissue iron in tissue in the form of ferritin in these neurodegenerative diseases like MS and Parkinson's and Alzheimer's, and also sickle cell anemia, which I'll mention. Excuse me. We also have the susceptibility also reflects changes in blood oxygenation. So it's proportional to the concentration of deoxygenated blood in our deoxygenated red blood cells. And so we can use that to visualize veins. We can use that to look at hemorrhages and microbleeds, and also look at brain function, how the brain actually is working dynamically. We can also look at changes in the myelin content. That's the kind of insulation around our nerve cells, and that changes in diseases like MS, and also calcifications, which we find in cancers and epilepsy and so on. Next, please. So we've applied this technique of susceptibility mapping in a genetic disease called sickle cell anemia, which affects hemoglobin and causes our red blood cells to take on this unusual sickle shape, which you can see in the top right-hand corner. Click. And this is the team of people who we've been working with for this project. And we've been collaborating with people in Tanzania, in Dar es Salaam, in particular this neurologist, Dr. Mboka Jacob. And the reason we're interested in sickle cell anemia, it gives people really awful symptoms when their red blood cells turn into this sickle shape. So for example, they can't carry enough oxygen to their tissues, and they are susceptible to stroke, and they can have cognitive problems, thinking problems. Click. So we are interested because we think we can use susceptibility to look at this disease because of the changes in both iron, potential changes in iron, but also changes in oxygenation in tissues. And this is interesting because iron can accelerate neurodegeneration and can also, it's very important for cognitive function. So it's really interesting to look at changes in that. A couple more clicks, please, just to get to the end of this slide. Okay, so, and the reason we think we can use susceptibility to look at this is because, as I said before, the susceptibility depends on both the tissue iron content and also its oxygenation. Next slide, please. So in some preliminary results in looking at children with sickle cell anemia in Tanzania, we found that the susceptibility increases faster in children with sickle cell anemia compared to their healthy siblings. And so this is really, really interesting that in some deep brain grey matter regions, we actually get an increase in the iron content of those regions, most likely. And so that's telling us about some of the disease processes, this brain iron accumulation. Click. And so we can see the pattern of increased iron changes in the brain here in these deep brain grey matter regions. And then we can also look at changes in blood oxygenation. So the superior sagittal sinus is this big vein that drains the whole brain, and we can actually non-invasively use QSM to see the decrease in oxygenation in the brain overall in these children with sickle cell anemia. So you can see that that cluster of red triangles is lower, has a lower oxygenation than the cluster of blue circles from the healthy controls. We've also, so next slide, please. We've also used QSM to look at Parkinson's disease, and it's really interesting. We've worked with these doctors, Ramona Weil, who's a Parkinson's doctor, and Mina Wrighton, who is a geneticist. So we're combining the results from our susceptibility mapping with genetics, and we can see that there are regional changes in susceptibility in people with Parkinson's disease. But then what's even more interesting, click, is that we can also find a correlation between the susceptibility changes and specific gene expression. So in regions that have a different susceptibility in people with Parkinson's disease, we found genetic changes relating to heavy metal processing and also nerve transmission. So this tells us, it can give us information about some of the processes that might be driving the neurodegeneration or nerve damage inside the brain in Parkinson's disease. And it may give us targets for potential treatments to slow the progression of this disease. Next slide, please. This is some of our latest work, just to show that as well as getting structural maps of these electromagnetic tissue properties, we've had a big European grant, which we want to basically minimize the amount of time that people with disease spend in the scanner, so they don't have to lie there for ages and ages. And we've developed about a 6-minute scan that gives us not only these susceptibility maps and conductivity maps, but can also give us information about how the brain is working dynamically and how all the different brain regions are connected together. So we can look at brain activity, both conventionally using standard functional MRI, but also using looking at changes in these electromagnetic tissue properties. So we can see oxygenation changes using functional quantitative susceptibility mapping. So this gives us a huge, rich array of multimodal structural and functional information in just 6 minutes of someone with a disease like Parkinson's or Alzheimer's lying in the scanner. So we're really excited about what changes this new sequence might show. Next, please. Of course, none of this work happens alone. We collaborate not only with doctors, clinicians, clinical researchers, but it also happens with the efforts of a big team. So this is the team from a few years ago, and we also need a lot of funding to do this research. So here's some of the funding that's helped us to do this exciting research. Thank you very much.
Hello, everybody. It looks like I am next. So, yes, hello, everyone. My name is Dr. Charlotte Maughan-Jones, and I come to this presentation with a slightly different background and maybe career trajectory than everybody else, but hopefully I can demonstrate to you that medical physics is kind of for everyone, regardless of your background. So next slide, please. Unfortunately for Camilla, I didn't take off any of the animations on this. So if you just scroll through until you get to the end, that'd be great. But essentially, my bit of a background is that I was a sort of standard animal loving kid who dreamed of being a vet. And I was very lucky to be also a classic high achiever at school, classic nerd who very much got a place at vet school and was very, very delighted at that fact. But when I went to vet school, I went to the Royal Veterinary College to study veterinary medicine. I struggled really massively in my first and second year. I found it very, very difficult to adjust to that and found the material really, really hard. So, for example, I went from being a high achiever, constant A's and A stars, to going to vet school. And in my first year, to pass, you had to get 50%, and I got 51.75%. So I was very, very average, which was quite hard hitting. So I decided to do something called intercalate, which is where you take a year out of either your veterinary, your medical, or your dentistry degree, and you go and do a year of another degree. And I, for some unknown reason, decided to come to UCL to do my intercalation in medical physics and bioengineering, which I had an absolutely fantastic time doing. And then after, returned to finish my veterinary degree at the Royal Veterinary College. So after returning there, I graduated as a veterinary surgeon in 2011, and then moving on, spent 4 years working as a equine, also known as a horse vet. So on the screen, that little person, I can't point with my arrow, but the little person doing the surgery sort of in the further background, that's me. But I knew that it wasn't something that I wanted to do for the rest of my life for whatever reason. So I started my PhD in advanced X-ray imaging in 2015, terrifyingly over 10 years ago now, in the same group as Sandro, and was awarded it in 2019, and then continued with the X-ray imaging research after that. And you can probably tell from the pictures that there's been an addition of a couple of children along the way. And then the current picture that's just come up is the third addition of a child was occurring at that point in time. But during this time, I also found a real passion for public engagement and working with schools. So I do a lot of that to try and encourage people like you to do the kind of things that I do, which is cool. Then after my PhD, you can go on to the next one. I spent 18 months as a lecturer in biomedical engineering in East London at a different university. And then the final part of this slide is that I now work back at UCL as a lecturer in engineering education. So I work more in the education space than I do in the research space. However, I spent 9, almost 10 years working in the research space. So I'll tell you a little bit about my time in the Department of Medical Physics. So next slide, please. So you've already heard from Sandro about this wonderful magical thing called X-ray phase contrast imaging. So I'm going to break it down just a little bit more. He's told you a lot more about the technical side of things. I'm going to go back to basics. So conventional X-ray imaging system, if you were to be referred to a hospital for an X-ray by a doctor, this is the kind of setup that you would expect to see. You would have what we call an X-ray source somewhere, normally above you, but sometimes behind you. Then there would be an X-ray detector, which might be underneath a table. And then you as the patient would be asked to lay on the table or put your hand or your leg or your foot or whatever it is on top of the table. Yeah. Now, the reason that we can see things on an X-ray is basically because X-rays are fancy shadows. So if I were to hold up a torch and put my hand in front of that torch, we would get a shadow, right? We all know that. That's like year 3, I think, physics, that is. Light travels in a straight line. We know that. And the reason that we get a shadow is because our hands are really, really good at stopping the light from traveling through it. And if you now replace a torch with an X-ray source and you put a body in front of it, or you put some object in front of it, parts of that object are, just like your hand with a torch, going to be incredibly good at stopping the X-rays from traveling through it. Whereas other parts aren't going to be quite so good. A bit like a window is really terrible at stopping light traveling through it. So you end up with what essentially is an X-ray shadow. So the areas that stop the X-rays from traveling through them are your bones, and the areas that don't are things like your soft tissue. So things like all your organs, the tendons, muscles, all the kind of soft, squishy stuff that exists within your body. Really, really rubbish at stopping X-rays from traveling through it. If you bring the next picture up, Camilla. Thank you. So to enable us to see some more of those soft, squishy things, like Sandro was saying, with mammography, trying to look at breast tumors as one example, is we know that as X-rays travel through your body, not only are they stopped or absorbed by certain parts, but they also change direction a teeny, teeny, tiny little bit. And we can exploit those changes in direction. So instead of measuring how much the X-rays have stopped or been absorbed, we're now measuring how much they have changed direction as they travel through your body. And the great thing about that is that change in direction is really much stronger in those soft tissues. So we can start to see all those soft, squishy bits that we couldn't necessarily see before. And as Sandro said, we do this by introducing some what looks like fairly simple additional hardware into our system. So we add in two what we call masks. So a sample mask, which sits between the source and the patient, and then a detector mask, which sits basically on the X-ray detector. And what that enables us to do is measure those changes in direction and enables us to see stuff that previously we couldn't. Now, that change in direction, that's probably something that you have already learned about at some point. Again, I think we're probably talking about year 9 or year 10 physics. And that's the process of refraction. So it's exactly the same as the creation of a rainbow. So next time you see a rainbow, that is the physics that we are using to create these images. So next page for me, please. Oh, yes. And if you want to know more, I forgot I put that on there. I did a podcast with one of my former colleagues about this imaging modality. So if you want to know more, please feel free to scan that QR code and listen to the Health in a Hand Basket podcast. Next slide. So what does that do with my research? So Sandro has already told you a couple of things that he has done and that his group has done, and I have in the past been a member of that group. But I wanted to bring together my previous career as an equine vet and my current interest in medical physics together in research. And we tend to think of medical stuff as being purely human, but there are animals as well. So if you have an interest in that side of things, there's really the opportunity to be able to do that as well. So what do horses and athletes have in common? Well, one of the things they have in common is that they are actually incredibly both incredibly prone to tendon disease. So tendons are the parts of your body that connect the muscles to the bones and help you move, help your joints move. And humans and horses are both incredibly prone to those. Luckily for us, in the horse, something called the superficial flexor tendon, superficial digital flexor tendon, or SDFT, is a really, really great model of human disease of the Achilles tendon. So we can use ethically sourced horse tendon material to study human tendons, whilst also benefiting both the horse and the human. So it's a bit of a win-win situation for us. Unfortunately, the reason that we want to look at tendons a little bit better is we currently don't actually have many, if any, evidence-based treatment modalities for tendon disease. So lots of you on this call probably have maybe had a tendon injury or know someone who has, and you might go to the doctor and they might tell you to rest or put some ice on it or put some heat on it, but none of that's really evidence-based. And that doctor will never be able to actually monitor how well your tendon is getting better. We don't have great ways of looking at tendons. The ways that we do have are subjective, or the resolution, so how small a detail we can see, isn't great. The other part of that is we don't have evidence-based treatment because we have no way of actually seeing disease or recovery of the tendon very well in the laboratory to develop these things. So here You can see an image on the top of a horse hoof. So that's basically the equivalent of the tip of our finger. And the bottom, a human foot. And you can see the bones beautifully, really beautifully. And you can kind of see a bit of a fuzzy bit of grey where all the rest that is essentially tendon, skin, and everything else is. We just can't see it. So next page, please. So what my research has been looking at, or was looking at, is how we can use phase contrast imaging to start to explore the microscopic and macroscopic anatomy of a tendon to help us gain a greater understanding of how tendons work biomechanically. If we don't know what they look like internally and their 3D structure, we're kind of missing a huge piece of the puzzle here. But it's also to help us watch as they are damaged and as they repair themselves, so we can see what processes they go through. So again, if you want to know a little bit more about the research that I did on the tendons, then please feel free to, again, follow that QR code on screen. And that's for a video I recorded for the department a few years ago. So final slide from me. What I currently do is I do a lot of teaching. So if you do join us at UCL to do medical physics, you will probably see my face about in some of the teaching spaces. And because of my background in clinical biology, I actually teach anatomy and physiology to medical physicists, which may sound like a bit of a niche thing, and I guess it kind of is. But I want you to understand the connections, the medical connections that you may have encountered in your friends or families, and relate them back to the technology that you're probably going to be working on within the medical physics field. So essentially, I'm hoping right now that you may even start to see some of the connections of things that you're doing in GCSEs and A levels, right? So if in your GCSE and A level, you've learned about the electrical conductivity pathway of the heart, you understand things like if I say sinoatrial node or atrioventricular contraction, you probably actually understand how a cardiac pacemaker works. If you understand things like action potentials and you understand how a nerve transmits pulses down from your brain to your finger, then you've kind of got the basic gist of what electrical stimulation is. If you know a bit about cell biology and the cell cycle, and trust me, that stuff is boring, but if you know a bit about that, then you also actually know about how cancer is both generated and treated. And if you know a tiny little bit about like the chemistry of bones, so like just the concept of calcium existing, then you can also understand how X-rays are created and how we get the contrast. So hopefully you kind of can see the connections to things that you're already learning. And hopefully you can already see that even if medical physics seems like a subject that's a little bit abstract to you at the moment, you are essentially all basically medical physicists already, and you already understand a lot of the base level concepts that we need you to understand to be able to do this as a career. Thank you very much.
Hello, everyone. Let me introduce first myself. My name is Ilias Taktsidis. Please call me Ilias. I'm a professor of biomedical engineering. And if you join UCL on year one, you're going to see my face as well, teaching some of the modules in physics, medical physics. And what I'm going to do today is I'm going to introduce you guys to Metabolite, which is one of my group within the Biomedical Optics Research Lab at UCL. And our motto is engineering light to monitor the infant brain. Next slide. So first of all, who we are and what we do. The pictures that you see on the screen are pictures that we took from the hospital, which is down the road from UCL. This is the neonatal intensive care unit, where we do most of our applied research. And what we are a team of engineers, physicists, medical physicists, doctors at UCL that work together, all of us developing new light-based technologies to help diagnose and monitor brain injuries in humans, especially looking at newborn babies. So we work on techniques to study and research the human brain, including neuroscience and its function, using, again, infrared light, near-infrared light. That's a particular type of light that you cannot see with your naked eye. Next slide. But why we want to do these things? So what is our motivation? And hopefully I can sort of demonstrate that here. Again, the picture that I saw on the bottom left is a picture from the neonatal intensive care unit. And that baby in that picture is about 2 days old, is a newborn baby that was born with brain injury. You might see some of these wires coming out of this baby. Those goes to instruments that we have built and use in the hospital. So our motivation comes through a condition that is called perinatal hypoxic ischemic brain injury. Sometimes we refer to this as breath asphyxia. So this is when infants, when newborns are born and there is some sort of complication during delivery and they have been deprived by oxygen to reach their brain. So some of these babies, they would actually develop to be fine and they would have a full recovery, but some of them would actually die. Some of them will have cerebral palsy, and some of them will have also significant cognitive, developmental, and behavioral problems. And how we sort this out, how we actually support our clinical colleagues, how we solve this issue is a physics and engineering problem. So what we want to develop real-time, non-invasive instrumentation and methodologies that we can look at these babies' brains in the neonatal intensive care unit as soon as they are born. Can you move to the next slide? So let's talk about physics. And what we now going to be using is light. And as I said at the beginning, a particular type of light, infrared light. We know that white light is composed by multiple different colors, which means different wavelengths. So one particular wavelength gives you the color of the light. And in the visible light, we got our red colors, our blue and green colors, etc. But we also have light that we cannot see, non-visible, so that it will be either ultraviolet or near-infrared light. So what we can actually do is that we can take a light beam and we can split it into these very different light colors, these different wavelengths. And what we can do that, we can do this splitting by using particular components like prisms, or what we use in some of my instruments is diffraction gratings, and we have different types of diffraction gratings. So one of our plans is to take this light and sort of split it to all different colors. And the particular colors that are of interest are the ones that are the infrared. So this is beyond the red color, and you cannot see it with your naked eye. Can you move to the next slide? What is unique with an infrared light is the fact that it's transparent to the tissue. So this is a picture of my hand, and what you have from one end is that you shine a light, an infrared light. And what is interesting, you could probably see in this picture, is that you can see shadows, but not as much of the bones, but shadows of the vessels inside your fingers. So there is a reason that this is happening. This infrared light is absorbed by certain molecules within your vessels, and that appears as shadows into our eyes. Can you move to the next slide, please? So what is happening in the vessels, we have the hemoglobins that carry the oxygen. So as oxygen is carried by the hemoglobin, it's becoming oxygenated hemoglobin. And then when the oxygen is given to your tissue, it becomes deoxygenated hemoglobin. And when that happens, it changes colors. So hemoglobin changes colors. And we know this for many, many years. And some of the techniques and technologies out there, optical technology, have been used this to measure the arterial levels of oxygen using instruments on your fingers or your ears. So that's called pulse oximetry. But what we want to do that in the brain itself, not just on your finger or your ear. But we want also to move beyond this. So if we get to the next slide. So indeed, oxygen is carried by your hemoglobins in your vessels. But what is important in your brain is that we've got our neurons, they need that oxygen. And with these neurons, we have mitochondria. The mitochondria are the power factory cells that will use that oxygen, and they will also get glucose to generate energy. So your brain is alive, so your neurons stay alive, so your neurons can function, and so that you can have action happening. So every time you move your arms or your legs, every time you talk, you do so because your neurons say so. And for that, they need energy, they need oxygen. And what we can do with our technology is we can also measure what is happening to the mitochondria, how they use up that oxygen to produce energy. If we can move to the next slide. So that's the physics, that is the biology. Let's now talk about technologies. And what we actually do is that we build instruments to actually achieve these measurements. And I introduce here a couple of those instruments. So you can see the serial instrument on your left, and then also the Florence system on the right. But what we're actually doing is that we're using and modifying and expanding current technologies like the spectrometer. And the spectrometer is something that they use a lot in biology, in particular also in astronomy as well. And we modify that to look in your brain and to try to get optical spectra coming out of your brain so we can then quantify the oxygenation and the metabolism. And these are some of the instruments that we've built over the years. If we can move to the next slide. But let's see what happens when we take these instruments into the hospital. And again, I'm showing you pictures of studies that we're doing at the neonatal intensive care unit at the UCLH hospital, which is down the road from where we are based. So first of all, on your left, you will see a recent study that we did on a preterm infant. Those are babies that are born pretermly. So these are about the size of my hand. They are very small babies and very sensitive. So what we can actually do in this case is that we use our instruments that are non-invasive, they don't produce any radiation of any sort, and you can see some of the fibers, the black fibers coming out of the baby's head. And on the bottom, you see some of the measurements that we do. On black, you can see the signals that we measure the oxygen levels in the baby's body, that they measure the blood pressure of the baby, and they also measure what we call the blood flows as well. But what we can do with our instruments, we can measure what happens in the metabolism, and that's shown in the green signal that I'm showing down there. So that signal tells what is happening in the metabolism. And what was fascinating for our medical doctors is that they identify that metabolism is not stable. It actually changes quite a lot during the time that the baby is in the clinic. And importantly also, it tends to follow changes that happens to this baby's blood pressure or heart rate, which was quite interesting for them to discover. But beyond that, we also move into things like imaging. And what I'm showing here on the right side of the screen is some of the images that we can generate. So we can look at the function of the brain, so you can see what areas of the brain do what. So in this case, for example, when we do kind of a visual stimulation, we look at the back of the brain, what we call the occipital lobe, and we see the change in oxygenation showing in red, an increase in oxygen levels, but also we see an increase in metabolism happening at the back of the brain. On the bottom graph, the D graph, the D figure, you can see the images of a baby where it is engaging in a functional activation we call the kind of peekaboo activation. So, you know, that game that you play with your babies and you close your eyes and you say peekaboo. So that generates particular pathways in the brain. And what we can do with that technology, we can image those pathways and then we can see how the brain develops across the age. And the next slide, I think that's my last one. Yeah, that's it for me. Thank you.
Great, thanks, Ilias. So that's a good introduction because I'm also going to talk about using light for imaging. But just before I start, perhaps as Charlotte gave a little bit of background to how she got into medical physics, I'll mention briefly how I got into it. So I studied engineering and went on to design opera houses and concert halls, and in particular doing acoustic models of musical spaces. And did that for several years and then realized I was more interested in physics. So now I do acoustic modeling in this medical physics space. So that's the background. That's a slightly different route in. But I'm going to talk about this. This picture here is a picture of a breast scanner for breast imaging, looking for breast cancers. And it's based on some quite interesting physics. But perhaps before I tell you about the physics, I'll tell you about the motivation. So Camilla, can you click a few times just to get the next slide up? Yeah, perfect, thanks. So conventional breast imaging, there's various different ways it's done. And I won't go into all the problems, but essentially there's no perfect way of doing it. In X-ray mammography, it's uncomfortable and you just see a sort of 2D projection of a breast. Ultrasound, you can do it quite quickly, but you don't see the whole breast, a tomographic image of the breast. MRI doesn't work for everyone. Not everyone's compatible to go in an MRI machine. So we wanted to come up, if you click, Camilla, please. We wanted to come up with a new way of doing breast imaging that wasn't expensive, could provide nice high contrast images, could see what you want to see, good for diagnostic purposes, and had good image resolution as well. So one more click, please. So we built with colleagues in the Netherlands and in in Lithuania. We built this scanner, so you can see sort of at the bottom left, it says laser. There's a laser underneath there, and I'll talk about what that does in a second. On the right, you can see a water treatment. That's because the breast, which sits in that bowl, sits in a water bath. And that bit in the middle, click please, come on. Right, there it is again. So there, what you can see, you see the little black dots, they are the ends of laser fibers. So they're laser sources, they're light sources that will pulse light into that bowl. And the little gold discs, each one of those is a very highly sensitive ultrasound detector. There's also a few other things in there, like there's a way to get the water in, and there's a couple of thermometers in there to check the water temperature. So the physics that we wanted to exploit is this. So Ilias talked about how light can propagate into tissue, and he showed that nice image of the hand with the light shining through it. And you could see the blood vessels in that hand. Now, the reason you could see the blood vessels is because the light was absorbed by that blood, as he explained. Now, if you send the light in a short enough pulse, and I mean, some number of nanoseconds, so maybe 10 nanoseconds. So you send a very short pulse of light in. Where that light gets absorbed, it will actually generate ultrasound. It will generate a pulse of ultrasound. And that ultrasound will then propagate out, just like normal sound, propagate out of the tissue. In this breast case, it'll propagate out of the breast through the water, and we can detect it with the ultrasound detectors. And then our challenge is, how do we then form an image of where that sound came from? Because if the light is all absorbed by the blood vessels, if we can get an image of where that sound came from, we'll have an image of the blood vessels. So that's what we tried to do. So next slide, please. So I've got a little model here, and on the left, just drag it back to the beginning again, Camilla. So on the left, I've got a simulation, and it's got so I've just drawn some little blood vessels. And once the laser pulse is fired, then an acoustic wave will travel out. You can see this is an acoustic model. These are modeling acoustic waves, and those black dots in a circle, that's modeling those gold ultrasound detectors. So that's modeling our measurement, and we'll measure the acoustic pressure over time, so the sound fluctuations over time at all of those different detectors. Then we'll take that data and we'll put it in a computer model of the, we'll see it again, there we go. So at each of those little black dots, we've got a separate time series measurement. And literally an acoustic measurement, like you're hearing an acoustic signal now from me. It's the same physical phenomenon, just higher frequency. And then we'll take those signals and we'll put them into a computer model of this system. And if you click again, Camilla, hopefully the other side will come up. There we go. Whoop. And what we do is we run those signals backwards in time, and then we stop at the time when we know we pulsed the laser. And so what we should see is that these waves are going to converge back on where the source of the sound was, and so you can get an image of the blood vessels. So that's called the photoacoustic effect. It's the light photoacoustic, the ultrasound. And that's called photoacoustic tomography, so forming an image from the photoacoustic signals. So next slide, please. Come on. And there's some images. So these are projections. What we get is three-dimensional images. Here you're seeing projections. So if you like, looking from one side, and then looking from the top, and then looking from the side of a couple of volunteer breasts. And on the right, you can see that it's looking at different optical wavelengths. So Ilias talked about how the different wavelengths of different colors of light were important. You can see we can get slightly different images. So we can extract diagnostic information, for example, blood oxygenation, from these images. Okay, next slide, please. Okay, so just my last slide. So just sort of where does the physics come in? So what if you're studying medical physics, right? So what physics have we used in this? So laser physics, so that image in the top right is a big laser. So actually it's two lasers in one box. And you can see a big bundle of optical fibers coming out of it. Those were the ones that would then wire into the bowl that you saw earlier. To understand how that light would propagate, we had to build models of how light propagates through tissue. So we had to understand how light scatters and travels through tissue. We had to build the acoustic models, which you saw. In fact, the model I used for these simulations here is actually the same model we used with the data. So we built that ultrasound model. The ultrasound detectors, which you can see on the right underneath the laser, the little three gold ultrasound detectors, we think are the most sensitive ultrasound detectors that have ever been made. We think they're at the limit whereby they're detecting the fluctuations in pressure just from the fact that the water is not at absolute zero temperature. We think we're measuring thermal fluctuations in the water. So that was quite an interesting project, getting very sensitive ultrasound detectors. And then to do the working out of how this reversal in time gives us an image, to do the image formation, we had to do some maths and code it up. So maths and computing come in there as well. So I think that's me done.
Hello, everyone. Back at me. First of all, thank you very much to all the presenters. Actually, it has been amazing. You attendees, you're very lucky. You have a range of amazing professors talking to you today, and I have found that very informative and inspiring. And I hope you did as well. We have focused today on many imaging techniques, but of course, medical physics has many other examples. So keep an eye on these. Next slide, please. So what I want to show you is, if you feel inspired, or if this is a career that you think you will be motivated to take, this is something that you can do to start preparing for it, and this is how you can start your journey. We do have a couple of medical physics undergraduate degrees, a BSc and an MSci, and these are an excellent way of learning more about medical physics and get you prepared for, initiating that career in the field. Our uni or undergraduate programs, both the medical physics programs, are taught in collaboration between our department, medical physics and biomedical engineering, but also done by UCL Physics and Astronomy department, which means that you get a unique opportunity to learn from two very research intensive and world leading academic departments, and this will benefit your experience by offering you a wide range of networking opportunities within the field of both physics and medical physics. You will also learn from lots of practitioners and gain experience on how to tackle major healthcare challenges, participate in student projects, and so on. I have to mention that the medical physics program is accredited by the Institute of Physics. If you don't know what it means, this is an external objective quality stamp, if you want, that is given to our programs from the Institute of Physics. So it's done at national level. And it basically means that at the end of this degree, you have you can become a member of the Institute of Physics and you qualify for it. There is, as I said, a couple of degrees that you can take. One is the BSc, which is 3 years, and the other one is MSci, which is 4 years. The first 2 years are the same, and you can swap between them in the first 2 years. Next slide, please. So what the program will give you is a very strong physics background in years 1 and 2 with core modules, and you will continue with advanced physics topics in years 3 and 4 using the optional modules, which in here are represented with light blue, and these are being taken with the rest of the physics students. You will also take specialist modules in medical physics, starting with some fundamental modules in year 1 and year 2 that you can see here in dark blue, and then continuing with more advanced modules in year 3 and year 4 that you will take as options as well. So you can really tailor your degree to the areas of medical physics that you're more interested on. You will also get experience in group and practical work in dedicated practical modules that we have across the years 1, 2, and 3, if you're doing the MSci, as well as labs related to many of the other modules in medical physics that you run. And you will experience research from year 1, starting in a small group project in one of the year 1 modules and going towards the individual research project that you will take in your final year, and where you will be embedded in one of the research groups within the department. So you might end up working with Sandro or with Ben or with Elias or Karin, any of our presenters. And going back to one of the questions that we got in the chat, how are our links with hospitals and how students benefit from it? Well, the connections with the hospitals are embedded within our modules. We will, the material that you learn will be informed by the research that our researchers are doing, so the state of the art in each of the fields, but also we get clinicians to come and talk to you. And when you do research, you will be working alongside the research groups in our department. And so that collaboration with the hospitals is it's very important, and you will be part of it. There is also internships that can take place during the summer. There are different ways in which we can offer you internships, and that is something that you will be able to access as well through this program. If you want to know more about the programs, I will refer you to the prospectus in the next slide. You have 2 QR codes that you can follow. And we're going to send you this slide so you will be able to see that. But next, you can also see how you can further contact us with questions. You can either contact me. I am the program director for medical physics. We also have Dr. Agostino Stili, which is the undergraduate admissions tutor. Or you can talk directly with current students using the QR code provided there. So I really hope you enjoy the seminar, and I hope this has helped you to know a little bit more about what is medical physics and how it can improve lives through science and innovation in medical imaging, diagnosis, and treatment. And if you have felt inspired by our speakers today or wonderful professors and researchers, and you want to join the field of medical physics, then I encourage you to apply to one of our courses, and hopefully I'll see you soon. There is a little questionnaire and survey that we will appreciate you to complete. And I think that is all the presentations that we have. Now I'm going to open the floor to questions. You can write your questions in the chat and we will do our best to complete it. So you can ask questions to any of our presenters or anything in general that you want.
Pilar, there's a few questions in the chat. I don't know if you want to address those.
Yes, I am going through it. Is there any that you want to talk to? It says, as a student taking chemistry, physics, maths, will I be able to study medical physics? So to study medical physics, you need to have A star AA with A star required in physics or maths. Both of these subjects are mandatory. So in principle, with the subjects that you have, yes, it should be fine. What extracurriculars or supercurriculars will be beneficial for this career? Really, The entry at the moment is based on the grades, so good physics and good maths. Extracurriculum activities, anything that is anything that develops your analytical skills, people skills. I mean, this is something that we talk more during the program, but does anybody want to chip in terms of extracurriculars? I think the program already offers you a very solid foundation.
I would say that any extracurricular or supercurricular that brings you joy at this stage is worth doing. So there are lots of things that you'll be doing within your degree where you maybe work in teams or anything like that. So even, for example, say you are a member of an orchestra, that is going to give you really great a great experience of working in a team, for example. So yeah, anything that brings you joy at this stage. I saw someone asked about biology side of things, and extracurriculars that you can do for biology. If you're particularly interested in those kind of things, and there's normally volunteer opportunities within various spaces. So obviously I come from a veterinary background, but there's always lots of volunteer opportunities within kind of clinical veterinary spaces and potentially within clinical human spaces if you're particularly interested in those sides of things. But don't worry about those things. You will very much get up to speed very quickly. So do things that bring you joy.
Someone is asking whether it's a problem not to have biology at this stage. The answer is no. We will teach you whatever biology you need to know. Thank you, Harvey, for your feedback. Yes, and again, talking about biology, what I would like to do is I'm going to go back to our presenters, wonderful presenters, and I'm going to ask for a piece of advice or encouragement, to finish this. Should we start? I'm going to go through my list in here.
Pilar, just before you start, I'll just have a look, and there is a Q&A, and in the Q&A you have two questions. If you click the button in Zoom and Q&A, you will see two questions there.
Oh, okay. Oh.
So it's next, did you see that?
Yes. Do you have any open days coming up where we can visit? Yes, absolutely. So what we are going to do is Camila, who is our communications officer, will be in contact with you and will send you the slides, and also will send you information about the upcoming open days. So you can actually come and see our lab, see your department, talk with us in person. That will be wonderful to have you there. And then someone is asking, what are the benefits to taking medical physics course as opposed to taking a different course and getting into the job market that way? There are various routes to join a career in medical physics. Typically, and in the past, or at least the way I did it, was studying physics, so a science degree first and then getting into medical physics. But I have to say that was because medical physics was not offered where I study. If you are interested in medical physics and you study directly medical physics, that is going to better prepare you for when you graduate to jump into things and actually get started with doing research in the field directly. So that would be my recommendation. Obviously, there are people who study medical physics and they then move into different pathways. This degree actually offers you the same knowledge as a physics degree, so it will prepare you for a range of careers that require data analysis, critical thinking, problem-solving skills. It will give you those tools that are very important for medical physics, but also other fields of research, other fields of work in industry and so on. What question? What is the biggest difference between the biomedical engineering course and the medical physics course? There is a lot of overlap. there is people who moves in and out from these careers. But if I have to pin down or kind of like try to explain the difference, I will say that the medical physicists are the ones that will look into the physical properties of material, tissue, radiation, and will see how it can be applied to healthcare and actually devise new treatments, new equipment, and so on, while the biomedical engineers will be the ones that sit down and make the circuits, make the equipment. And of course, there will be a lot of interaction between them. But yeah, I guess that is the main difference. Thank you, Camila, for putting there the open days. Am I missing any question, Tim? So while we wait, Sandro, do you want to give us final remarks or final advice or final comments?
Well, maybe just to say that if you're into applications and application to human health or discovery-led science as well, we do a lot of stuff which is basic science with an angle to solve big problems in medicine and biology. This is the place to be, and even though it's primarily applied, many of the stuff that we do is quite groundbreaking. We have this idea of looking at things in a radically different way rather than just improving the existing. We have a number of examples across the department where we have created genuinely new science. So yeah, you can find a bit of everything. And if you're interested in the field, come and speak to us. Thank you.
Thank you, Sandro. That's absolutely true. Who was next? Was it Karin?
I can go next. I would say that one of the advantages of doing medical physics as opposed to just straight physics is kind of well representative of how I felt. So I had read all these books about particle physics, and it's fascinating, but it's kind of the applications are sometimes years away or sometimes never, sometimes very theoretical. And for me, the attraction of medical physics is that you've got fascinating physics, really fascinating physics, but you've got a potential to really make a difference to people within your lifetime. So for me, that's what attracts me to medical physics and makes it exciting. And as Pilar said, you've got both all the knowledge and background that you would get from a physics degree, but then you've got that real kind of connection with making a difference to people today.
That is lovely. That's lovely, Karin. If I wasn't in medical physics, I will join right now. Who was next? I think it was Charlotte.
Yes, it was me. Yeah, so what would I say? I would say that the thing that I love about medical physics is there is room at the table for everybody. You get people from all different backgrounds and walks of life and interests, and it makes for a really interesting place to exist because you will collaborate with people and speak to people who you never thought that you would speak to, and everybody's voice is equally as important. Ultimately, the clinicians can't do their job without the medical physicists, and the medical physicists can't do their job without the clinicians. So it's a really, really wonderful place to exist. And don't tell anyone, but I don't have an A level in maths, and I've still somehow ended up getting this far. So, so there really is a room for even the mathematically illiterate. So yeah.
Yeah, that is true. We took you and then we taught you the maths, isn't it? Yeah. Elias.
Just to echo some of the things that already said, if you want to do a medical physics degree, this will give you the capacity to have a hands-on kind of role in healthcare. So you can get your fit into healthcare. So you can get your foot in helping people, and this is about for people that like to apply physics with real world consequences effectively. So you take your physics and you really apply it to something that people care. That is my take-home message.
Thank you. And finally, but not least, Professor Ben.
One comment first. So on the biology question, I have no qualifications in biology. So that's not essential. But maybe just a final piece of advice, maybe it's quite broad, but read widely and read a lot. That's what I'd say.
Excellent. I think I echo that actually. So when the students are in the program and they start looking for the optional modules, we always say, don't go for the easiest, go for the thing that interests you the most. And for that, you need to see a range of things. So yeah. Excellent. So I think I'm gonna close it there. I don't see any other questions. If you do have further questions, please contact us. We are very approachable, as you can see from today in here. But yes, I hope you enjoy it, and thank you again for coming and staying with us this afternoon. Bye bye, everyone.